Hello, I'm sorry for the delay in posting this lecture. I've always used a combination of blackboards and slides. And this lecture in the past I've used the blackboard quite a bit. So it took some time to transfer what I used to do in the blackboard over to the slides. So we continue with lecture E. What I want to now do is talk about something called the CDF, cumulative distribution function, also known simply as distribution function. And what this says is it's a function of baby x. And what it says is it gives you an equation that gives you the probability that some random variable is going to be less than or equal to a particular value called baby x. And going forward, you use big F to denote CDF functions. So if you see a big F, it's understood that you're talking about the probability that something takes on a value less than or equal to some number, as opposed to baby F, which is density, and baby P, which is probability mass function. So if you're working with discrete random variables, the way to calculate whether a random variable x is less than or equal to some particular value baby x, you would sum up the probabilities all the way to baby x. If you're working with continuous random variables, you would integrate in theory from minus infinity all the way to x. Let me do an example here. This is not a function, it's simply giving you a numerical value for the probability that some random variable is less than or equal to some number x. Here you have a PMF. Notice it only takes on masses at discrete random variables. And here you have a density, or which is defined from minus infinity to plus infinity for a continuous random variable. Over here, somebody says, give me the probability that the random variable x is going to be less than or equal to 2. So ultra technically, the way to think about this is that there is no mass defined over here. There's only positive mass where there is in fact some probability. So if you want the probability that x is less than or equal to 2, you should really be asking what's the probability of minus infinity, minus 10 trillion, minus 10 billion, minus 199, minus 1, and so forth. So you can see that all those probabilities from minus infinity to quote unquote minus 1 for integer values would be 0. Once you hit 0, you can see that there's some mass. So you would add the probability of 0 plus the probability mass at 1 plus the probability mass at 2. And this would give you the probability that this random variable x takes on a value less than or equal to 2. The same way, what's nice about continuous random variables is that they go from minus infinity to plus infinity. So if somebody says, give me the probability that the random variable x is going to be less than or equal to zero point 0.5, you're then looking at the area under the curve to the left of zero point 0.5. So you would theoretically integrate from minus infinity all the way to zero point 0.5. I said theoretically because when you actually carry out the integration, it really depends on how the function is structured. I'll give an example in a few minutes. These are numerical values of probabilities being less than or equal to some number. What about a function? Well, you can imagine that there's an arrow here. So if I ask you what's the probability of that the random variable x takes on a value to the left of this laser pointer, you would say 0. If I move it here, it will still be 0. As soon as it hits 1, the probability that x is less than or equal to 1 becomes 2/8. So you can see there's a jump right here. As the needle moves this way, the probability that something is less than or equal to this number at laser pointer is still 2/8 until it hits 4/8. So you can see that the CDF is starting to become a function of x. For any time the values of x is less than 1, strictly speaking, this number is 0. If it's between 1 included all the way to 2 excluded, it'll be 2/8. From x is equal to 2 included all the way to x is equal to 3 excluded, it'll be 6/8 and so forth. So this now becomes a function of x in the sense that the value of this graph right here, the value depends on where this laser pointer is, the value of baby x. Now you have a continuous random variable. So you have a density function over here. If the laser point is here, the total probability that x is less than or equal to this number right here is 0. As laser pointer moves this way, I wish I had two laser pointers simultaneously. Right? As soon as it hits over here, this starts to take on some value. And as my baby x moves this way, you can see the CDF also moves this way because now I'm calculating the areas under the curve. So now it starts to rise like this. This also starts like this. Because CDFs gives you the total probability of being less than or equal to a certain number, by definition, the CDF will never be lower than 0 because no probability is lower than 0. And that's this CDF, the value of this will never be greater than 1 because probabilities can't be bigger than 1. So this is kind of sneaky. If you actually look at this picture very carefully, notice how the density, as I said last time, is a number that can be greater than 1. Right? So if you have a PMF, these masses are represent literally probability. So these heights will never be bigger than 1. On the other hand, this height does not represent probability. Remember that for continuous random variables, it's the area under the curve that represents probability. So the heights don't represent a probability. So therefore, you can see it's possible for the density to be bigger than the value 1. See, we have number 3 over here. But CDFs, since they represent a probability, will never be a number lower than 0, never be a number bigger than 1. And this allows us to do something interesting. So here's a definition of CDFs. The CDF by definition cannot be a decreasing function. As the value C goes up, as you move from left to right, as I move from left to right, the CDF either goes up or stays flat. It never goes down. That would be impossible, right? Because that would mean that if it were to go down, somehow there's negative probability as you go over here. That hasn't happened yet. So if a number A is strictly less than a number B, then the total probability that something is less than A will be less than or equal to the probability of being less than or equal to B. You notice that there's a greater than inequality here. There's a less than or equal to inequality here. And you should ask, if that's the case, can I draw a picture which would match these two scenarios over here? It's very easy to do. As I just mentioned, CDFs can never be the less than 0, cannot be more than 1. The fact that a CDF has always been 0 allows you to use Excel, for example. I wish we had more time. We could do some really fancy finance and mining uncertainty decision-making problems, whether to drill for a mine with all kinds of uncertainties. And one of the most common tricks people use in finance is Monte Carlo simulations. You can do exceedingly hard problems with a simple random variable, which I'll explain how this works in a few seconds. And of course, the probability that x is bigger than some baby x is, of course, so the probability that you are bigger than some baby x is 1. That's the whole area of the curve minus the probability to the left. That's exactly what you see here. And the chance that the x is between two values a and b means that you can find it as total area probability of being less than b minus the probability of being less than a. What's left over, of course, must be the slice in between, or the probability of being between a and b. As I mentioned, you can use computers to simulate distributions. So here's what I mean. Supposing you actually have a CDF given to you here. It represents some PDF behind the scenes. Here's the equation, x cubed as long as x is between 0 and 1. If you want to simulate the PDF, so if you imagine you have a machine, a computer, that now picks numbers from the underlying PDF, one way you could do it is that you could say, okay, fine, since this number, CDF, literally the probability of x being less than or equal to some baby x, is a number that's never less than 0, but never more than 1, you could go to Excel. And in Excel, if you actually type in equal sign, RAND, open brackets, close brackets, nothing in between, if you press enter, it'll generate a number that's always between 0 and 1, right? And you know that x cubed is always going to be a number between 0 and 1 because it represents literally the probability of the random variable x being less than or equal to some baby x. So because x cube is a number between 0 and 1, let's use baby r to show that it's a number between 0 and 1. So notice, given the CDF, I can now start to use a machine to actually draw values of x from the underlying distribution, even though I may not know the distribution right well. I kind of don't, because what I've done is I've solved out for x cubed, right? So if I now rearrange, I can now start to pick values of x from the underlying distribution, which by the way was 3x squared. You should ask yourself, why can't we do this trick from the density, right? Why can you actually simulate any PDF from the CDF by using random numbers between 0 and 1? Or why can't you do that for the PDF? Think about this. The answer has to do with the fact that CDFs are between 0 and 1, so you can use machines to pick a number between 0 and 1. PDFs may not be a number between 0 and 1. That's why you can use machines to, you can use a CDF to then simulate the X values from the underlying PDF. Let's now try to do a CDF of multiple random variables. This is going to be horrible beyond belief. Life sucks. Here's your good old joint density that we introduced, I believe, yesterday. Someone says, given this joint PDF, derive the joint CDF, meaning that what's the probability that random variable x takes a value less than baby x and at the same time takes on less than value baby y. So you're looking for, actually, let me not mess it up. Less than x to the left of this bar right here and less than y. Since the density is only defined with a gray area, you want the total probability that pick any point xy. It could be on this edge right here, could be inside, could be over here, could be there, could be anywhere. Once you pick it, you want this total area of this thingy wingy over here. I can't even call this a trapezoid anymore. God knows what it's called. I don't know. Right? This whole thing. So you're going to go bonkers if you try to find, unless you break this problem down. If you have an xy over here, notice it breaks up into a triangle and a rectangle. That's what it's over here. You want to find out the area on the triangle. There's a surface over here, equation 3x. What's the area under the surface for this triangular region over here, A? And what's the area under the surface for this rectangular region, B? One of the reasons you can think about this is that here, once you pick an x and a y, notice that in this region A, baby x must take on values between 0 and this number. But this number, of course, is whatever value y you had over here. So that's why you'll notice that x must lie between 0 and y, because once you pick a dot x and y, as you start to integrate under this surface for that triangular region, you have to remember that if you're going to integrate across the x values first and the y values later, to remind yourself that x can not be a number, it has to be a number between 0 and y. That's exactly what you see here, 0 and y. And then y, if you for any value of x you pick here, y has to be between 0 and that particular value x. So if you picked a value x over here, you have to be between 0 and x. That's exactly what you see over here. Right? It's a bit confusing because sometimes it's hard to know which x are we talking about. But this x is referring to some arbitrary x over here. So if you want, you can call it x like this. So that gives you this thing right here, right? So when you do the whole integral, and you should do this, you get y cubed. So the whole area over here is y cubed. Now I want this rectangular region. Now notice over here, let's change the color. Let's use a pen. Notice that over here, if you're going to integrate across the x's first and then the y's, the x values have to be between y and x. That's exactly what you see over here. That's exactly what you see over here. Again, little bit confusing, but that's okay because it doesn't matter what symbols we use. And once you integrate from x from y to x, y must go from 0 to y. So y must go from 0 to y. And again, I integrate the joint density and I get this answer. Sum the purple thingy, that's the triangle, plus the green thingy, that's the rectangle. And then of course you get the CDF. This give me any value x and y, and this expression picks up the total probability of finding an outcome that's less than the value x and simultaneously less than the value y. And anyway, now here's another nasty one. Here's a joint density of three variables, x, y, z. And somebody says, give me the CDF. So you're now, x, y, z can take any value between 0 and infinity. So pick any point in R3, any value. X could be 1 trillion, Y could be 3, Z could be 0.0001. What's the probability of finding a point X, Y, Z less than or equal to that value X, Y, Z I just read out? So you want the CDF. By definition, you want the joint probability of random variable X being less than or equal to some baby X, random variable Y being less equals to a particular value y, and random variable z being less than or equal to some particular value z. In theory, this would mean you have to do a triple integral of the joint density of minus infinity to x, y, z. So of course, now what I do is I bring the expression in, sub it here, and you have to do this. Now you could do this, by the way. I mean, if you actually, so the way you could do this is you could go to Wolfram Alpha. You could ask it to do an integral, three integrals. Of course, uh, you have to remind yourself that this expression only exists from x, y, z from 0 bigger than 0. So when you do it in Wolfram Alpha, or if you do it by hand, you would have to put 0, 0, 0 over here and carry the integral and give the right answer. Or you could do a trick. You will notice that it is almost that this joint PDF was a product of three other PDFs, because notice that this is equal to minus x times minus, sorry, this is equal to minus e to the power minus x times e to the power minus y times e to the power minus z. It's almost as if like e to the power minus something is a PDF unto itself. And if they're independent variables, you can now, the joint density can be found by multiplying each of them together, right? So this would then be equal to e to the power minus x times e to the power minus y times e to the power minus z. So since they're independent, you could play the same trick over here. This joint probability by quote unquote independence would then be broken down in the products. So it'll simply be the chance of x being less than or equal to x times the chance of y being less than or equal to y times the chance of z being less than or equal to z. So now you could find out the CDF of just x, multiply by the CDF of just y, multiply by the CDF of just z. Sorry, I missed a, this should have been a bloody, sorry, 0 over here, because I'm going to carry this thing out right now in a few seconds, okay? And so if you want to know how to compute any of these, I've done it for you. Pretend that you're now calling these things a W. You want to find this creature right here. Reminding yourself that this e to the power minus something is only valid for when the random variable takes some values from 0 onwards. The lower bound of the integral would be 0, upper bound would be W, right? Because you're trying to find out the probability of being less than or equal to some number W, and you would take this integral. And then the answer would be something like this. So the answer to this would then be 1 minus e to the power minus x. This one would then be 1 minus e to the power minus y, 1 minus e to the power minus z, and so forth. And that's exactly what I've done over here. So the CDF is exactly what you see over here, right? Pretty straightforward. So you could have done it like this. It would have required a lot of work, or you could have actually realized that these things are in fact are independent variables and then use that trick over there. Now we go to some exercises. This is really important, especially people in finance, right? Because you often have things in stock markets and you have functions of those variables. For example, you could have the highest price observed in any month. You could have average returns, you could have median returns, and often, if you read John Hull's book, Options and Derivatives, for example, right, or for that matter, if you read a book by, let me try and find this book somewhere here. Damn books are never be found when you need them. Actually, 1 second. So you could Options and Derivatives by John Hull or Investment Science by David Leuenberger. Amazing books, lots of probabilities, lots of stats, lots of juicy stuff for anyone who wants to go into buy side, right, or risk, or heavy duty quant investments. You're going to be given a CDF of a random variable, and from CDF, find the PDF, or quote unquote the PMF. The way it works is the discrete case is the simplest one. If I gave the CDF to you, then you knew that the probability of x is equal to 0 was 0. The probability of x is equal to half was 0. And you can tell by the jump that here that the probability of x is equal to 1 must have been 2 over 8. That's why it jumped here. You can deduce that the probability of 1.5 was 0, and the probability of 2 had to be equal to 6, sorry, the distance over here, which is the difference 6/8 minus 2/8, or 4/8. See, right here. Because each of these things are jumping up by the probabilities that you see over here. So you can see that the quote unquote change in CDF divided by change in X gives you the quote unquote probability function. So if you now extend this to the continuous case, it shouldn't come as a surprise that the change in CDF over change in X is equal to a PDF. But you could have also seen this directly from the definition of integrals, because the this is in fact, if I differentiate both sides, I'm just taking d CDF dx. If I differentiate the right side, I'm taking the antiderivative. So the derivative would cancel out with the integral, which is the antiderivative. It's like proton and actually, sorry, mass and anti-mass, or whatever, right? So the two things would collide with each other. Derivative, antiderivative, poof, disappears and gives you the PDF. So it's not that difficult to see that, right? So if you were given a PDF, all you have to do is, sorry, if you're given a CDF, all you have to do is, if you want to get the PDF, the density, simply differentiate with respect to x. So if I take x cubed and differentiate with respect to x, voila, I get 3x squared. That sounds really easy. Well, it's easy because it's not that easy, because the trick, of course, was you can only do this for where the CDF is defined. And it's defined from 0, x is equal to 0 to 1. So this creature 3x squared only works from 0 when x is between 0 and 1. If you try to plug in, it won't work for x is bigger than 1, nor will it work for x is less than 0. In fact, you can prove to yourself this is in fact a legit PDF by integrating this curve from 0 to 1, and you see the area is exactly 1. Right? So the fact that you have to worry about these ranges is going to be important in a few seconds. So let me show you an example. You can extend what you just saw in the previous slide to many variables. Somebody gives you a CDF of many, many x's, n Nancy of those, and wants you to take the CDF of many variables and find the PDF of the same many variables. Then by the same logic you used before, if you found the PDF by differentiating the CDF, then you can find the PDF by differentiating the CDF. But the trouble now is that you have n variables, so you'll have to carry out this derivative n times. So what it means is, take the CDF, differentiate with respect to x1, then again differentiate that creature was left over with x2, x3, x4, x5, keep doing it. Ultimately, you will get the PDF. Example. We have already seen this joint PDF before. We just a few slides back derived the joint CDF, which we saw was this expression right here. It's like literally a few minutes ago. I want to know if I can go backwards by differentiating. If I take this animal and differentiate with respect to x, then differentiate with respect to y, you will see, and you should do this, you'll get back exactly what you see over here. And of course, remembering that both creatures are only defined for this range that you see over here. Here's another one. You remember this one? We knew the PDF originally. We derived the CDF by the little clever trick. Can I now go backwards? If I take the CDF and differentiate with respect to x, then respect to y, then respect to z, you will get back exactly what you start with in the beginning. So it works beautifully. Again, you got to remember the ranges. Now comes something slightly more tricky. 2 seconds ago, what did you do? You took the CDF of x and found the PDF of x. Or you took the CDF of many x's and found the PDF of many x's. Now what you have is something a little more tricky. Go back to a CDF of x. But this time, instead of finding the PDF of x, someone's asking you for the PDF of a function of x, which of course means that you can use the technique that comes of going forward can be used to find the PDF of x, because after all, the PDF, because x is a function of x, right? So this allows you to find the PDF of something more than just simply for more sophisticated functions. So for example, it could be x squared, x cubed, square root of x. The only thing you insist, of course, is that the relationship between y and x be a one-to-one relationship. You remember that we did this in lecture, God knows what. I think it was C something, one-to-one functions. Here's how we do it. Slowly. This is really crappy notation. I'm very sorry, but that's because I have to use a CDF of two creatures, and unless I put subscripts, it's not going to make sense. Someone gives you the CDF of a single x variable right here. Then someone says, listen, here's a random variable y, which is a function of x. So it could be x squared, for example, at 3x plus 2. And knowing the CDF of x, somebody wants you to find the PDF of y. Assume that this g function is one-to-one. If it's one-to-one, I can back out x in terms of y, so it gives you the inverse function. Here's how you obtain the CDF of y. Very, very slowly. You know already from this slide right here, excuse me, sorry, that I can always find the PDF of a single random variable by differentiating the CDF of a single random variable. So why don't we use that trick to our advantage? If I want to know the PDF of y, wouldn't it be wonderful if I found the CDF of y? Because once I found the CDF of y, I would differentiate with respect to y and get the PDF of y. So the journey begins. We want to really find out the CDF of y. So I put a subscript here to remind ourselves that right now we're looking for the CDF of y. It does not mean you are taking derivatives. For the love of God, this is the problem with open book exams. I bet you there are some people who's like, yeah, open book. I have my notes open. I'll just wing it, gangster style on Friday. And then you look at the slide, and then you may think I'm talking about derivatives. I'm not. I'm simply saying, let's look at the CDF of the y variable, because the reason you put this here is because what's it saying? It says, give me the probability that the random variable y is less than or equal to some specific value, maybe y. But the random variable y is in fact a function of x. Well, that means you're asking the probability that that function of x takes on a value less than or equal to some particular value, baby y. Remember, baby y is a number. Well, since it's a one-to-one function, I can re-express this as saying that's the same as asking what's the probability that the excuse me, the random variable x is less than or equal to some number. What number? G inverse y. Right? It's a number. But if I'm asking the probability that the random variable x is less than or equal to some number, I must now be asking for the CDF of x. But now, what value of x am I using? So normally you would use baby x here because you're looking for the probability that big X is less than or equal to some baby x. Your baby x now has become G inverse y. So now you would use the CDF of x, as hence the subscript x. But now instead of using baby x as a number, you would use G inverse y, the number. And once you get this is after all now behind the scenes, the CDF of y. What you're doing is you're using a CDF of x. evaluated G inverse Y to fool the system and get the CDF of Y. But once I have the CDF of Y, if I differentiate with respect to Y, I have the PDF of Y. Beautiful. Example. Someone gives me the CDF of X. It's X cubed, as long as X is between 0 and 1. You come along and say, what's up? Listen, Y is always equal to 2X. And you insist that I find the PDF of 2x for you. Now you have to start thinking a little bit more carefully. Things are not so pretty anymore. Here's a CDF of x for values of x between 0 and 1. But 0 and 1. But notice that y is equal to x. X is between 0 and 1, and therefore y is going to be between 0 and 2. So whatever PDF of y that you find out has to take into account that the value of y must now be between 0 and 2. I apologize, the scales are not, well, these axes are not to scale. So coming back to our problem, I want to find out the PDF of y, which is equal to x. Since this is a one-to-one function, I can express x in terms of y, and I know x is equal to y divided by 2. Let's start the story one more time. If I can only find the CDF of y, then I would take the CDF of y, differentiate with respect to y, and get the PDF of y. So my journey once again starts. I want to find the CDF of y. So again, the subscript here is just to remind ourselves that we're actually looking for the CDF of y, which by definition is the probability the random variable y is less than or equal to some number baby y. But the random variable y is of course nothing but 2x. So I'm asking, what's the chance that 2x is less than or equal to some number y? But that's the same thing as asking, what's the probability that the random variable x is less than or equal to number y over 2? But voila, I now will be using the CDF, because CDF says, what's the probability x is less than or equal to some number baby x? But now baby x now is equal to y divided by 2. So if I now see a CDF of x, which is x cubed, I would now replace x by y over 2. And instead of doing x cubed, I would now do y over 2 cubed. So y over 2 cubed is your CDF of y. And now if I take the CDF of y, differentiate with respect to y, anyone who makes a joke about y is, and let's not make bad jokes right now. CDF of y, differentiate with respect to y, gives you the PDF of y. And you should, of course, when you do this, you have to always accompany this with a range. This is only valid as long as y is between 0 and 2. You should try to integrate this thing between y 0 and 2 and make sure the error is equal to 1. Let's do a slightly different example. This is a very simple example in terms of, for those of you who are in MFEs, you can think of it this way. A a hedge fund or some fund or portfolio manager, whatever, observes the stock returns, Apple's stock returns for 3 months, always 1 to 3 months, 1 to 3 months, 1 to 3 months, 1 to 3 months, 3 months in a row. And let's pretend that the density of returns is 2 times x, where returns are between 0 and 1, right? That's the density. Now, here's the CDF. What's the probability that the returns are going to be less than or equal to some of baby x? X squared. Now what somebody wants is, you're somebody who follows Apple stocks 3 months in a row. Return number 1, return number 2, return number 3. Press the reset button. Return number 1, number 2, number 3, and so forth. What you want to know is, anytime you observe Apple returns 3 months consecutively, there must be 1 month where the return was the highest, the maximum return. So let's say you followed January, February, March. Maybe February was the highest one. So what you're looking for is the return, the highest return in any given 3-month period. But what you now want is, you know the distribution of returns in any 1 month. That's density right there. You know the CDF of returns in any Apple's returns in any 1 month. Now what you want to know is the PDF, the density of the highest 3 months returns. What was right of the maximum of these 3 numbers? So These three numbers, one of these numbers would be the highest in any given 3 month slot. You now want to find out what's the distribution of that creature right there. See what I'm trying to say? So you're a stock analyst following apples for 3 months consecutively, 3 months in a row, 3 months in a row, 3 months in a row. In any 3 month period, you want the highest returns. And now what you want to do is you want to find out what's the probability distribution of the highest return in any given 3 month period, right? So let's begin. I'm going to drop subscripts now because you have a pretty good grasp of how this thing works. You want the CDF of Y, the probability of random variable Y being less than equal to some particular value, baby Y, right? So it's literally asking what's the probability that the highest return in any given 3 month period is less than equal to some number, let's say 90%, right? But Y is, of course, the maximum of those 3 month returns. But if the maximum of these three numbers is less than equal to number Y, then each of those three numbers must have been less than equal to Y, right? If the highest of three numbers is less than equal to some baby Y, then each of those numbers must have been less than equal to some number Y. That's exactly how I jump from here to here. But now I invoke independence. Each of these things is IID, which means uh, identical independent distribution. So the joint probability, the same trick I played some time back, is e to the power x thingy wingies. The joint probability of being less than or equal to y is the probability of x1 being less than equal to y, x2 being less than equal to y, x3 being less than equal to y. And of course, these creatures, these CDFs, are given to me up here. These used to be x squareds, but now I have y squared here, y squared over here, y squared over here, y squared, y squared, y squared gives you y to the power 6. Once you have the CDF of y, differentiate with respect to y, and then the answer is here's the PDF of y, right? So if you are following Apple stocks over 3 month periods and you always record the highest return of the 3 months, then the distribution of those maximum those y's will be 6y to the power 5, defined over what range? Between 0 and 1, right? Because each of the x's is between 0 and 1, so the maximum must also be between 0 and 1. Pretty cool, I think. Of course, if you're going for advanced portfolio management, you might as well start asking the distribution of the minimum returns, mode returns, median returns. It can get really nasty. Highest minus lowest returns. Now we do something different. 2 seconds ago, I was finding out the PDF of function of x from the CDF of x. I was trying to find out the PDF of a function of x from the CDF of x. Now I want to find out the PDF of a function of x from the PDF of x. So now you're given a PDF of x. Now you're given y, which is a function of x, and asked to find out the PDF of this function. Since this is actually one variable, I call this a univariate Jacobian method. You remember the Jacobian matrix? Remember that? We did this in lecture B2, I believe? Or was it C something? Maybe C something. You already know that to find the PDF of a random variable y, all you have to do is find the CDF and differentiate with respect to y. And how did you find the CDF of y? You use from the CDF of x. You use CDF of x, but you evaluated that at g inverse y. Now, by the same logic as before, we're going to express this expression right here in a more, it was not obvious, but now I'm going to make it more obvious by re-expressing exactly what you see here in a more broader term, which in this slide doesn't make a difference. What you're about to see in red down here is identical to what you see up there. So in this, for the one variable case, it showing you the Jacobian method really didn't make a difference. But it will make a difference when it comes to the multivariate case. So the way it works is, excuse me, someone gives you a function of x and asks you to find the PDF of this function of x, i.e. PDF of y. But this time they want you to do it from the PDF of x. The way it works is, in words, to find the PDF of y, I put the subscripts on purpose to show this is the PDF of y. All you do is you take the PDF of x right here. I'll do it as a pen. Take the PDF of x, whatever equation you had, and instead of x, you now express x in terms of y. That's exactly what is here. So you have a density equation of x in terms of x's, take the x out, express them in terms of y's. And then what you multiply, and I really apologize, I didn't use this notation. Some dead dude probably made this up. This is, in fact, the quote-unquote Jacobian because it's the derivative. You differentiate x with respect to y, take the determinant, and then take the absolute value of the determinant. Sorry, guys, this bars mean two things simultaneously. Determinants, actually, they mean the absolute value of the determinant. How in God's name do you do this? Let's do it this way. We've already done this before. Remember how we had a density of 3x squared? We found this sometime back. Now, if you click on this link and you can find out. Could I have gotten the PDF of 2x from this PDF of y, which is 2 times x, from the PDF of x, which is 3x squared? Yes, I could have. The first thing I need to do is express x in terms of y's. I invert the function. X in terms of y is y over 2. Now let's go slowly. I want to find out the PDF of y from by fooling around with the PDF of x. Here's what I do. I take the PDF of x, which is 3x squared, and wherever I see an x, I express x in terms of y's. So what you'll do is you'll notice, excuse me, it's very emotional. I'm now going to express x in terms of y, which actually is equal to, right here, 3y squared, right? Because I've taken the x out and put y over 2 in, so that's your 3y over 2 squared. And now I multiply by the absolute value of dx over dy determinant. dx over dy is 1/2. The absolute value 1/2, of course, is 1/2. And then when I join everything together, I have my density, which is the exact same answer you got before. But of course, you have to remind yourself that if x was between 0 and 1, and y is 2 times x, then y must be between 0 and 2. Exact same answer, different technique, right? Because earlier, we use, sorry, I might have misspoken when I said this answer is exactly the same as this answer. Sorry, I take that back. But you do need this dx dy even in the single variable case, because here what you did was CDF to PDF. Here you're doing PDF to PDF. Now let's go to the multivariate case. You're given the PDF, the joint PDF of several variables, several x's. Excuse me. Sorry, let me have some water. And directly from the PDF of x's, you also find the PDF of y, which is functions of x's. So here's how the general algorithm works. Someone has to, if you have two random variables and you know the joint PDF in terms of x1, x2, if someone now asks you to find the PDF of y, they have to give you two separate y equations. One y equation in terms of x1, x2, a second y equation in terms of x1, x2. And what you can do is you can invert each of these equations, they're quote unquote one to one, and express the x1 in terms of y1, y2 from this equation, and x2 in terms of y1, y2 from that equation. And to find the PDF of y1, y2, take the PDF of x1, x2, and wherever you saw an x1, you would now express the x1 in terms of y1, y2, right here. Right? Wherever you saw an x2, you would express now in terms of y1, y2, because you already have those expressions from up here. And then you would multiply with the determinant of this Jacobian matrix, which of course is, the first row is x1's differential with respect to y1, y2. Second row is x2's differential with respect to y1, y2. Take the determinant of this expression, absolute value, and then you're done. Once you get the joint PDF, to get the PDF of just either Y1 or Y2 from yesterday's lecture, you integrate the joint PDF in terms of the other variable. So if you want f of y1, integrate the joint density across with respect to y2. If you want y2, integrate the joint density with respect to y1. Right? So let's do an example. So this is going to be nasty. Let's start praying already. The way it actually works is this mouse always has a habit. Sorry, guys. I like how there's no mouse. Okay, there we go. No lizard pointer. Okay. So what we have here is something like, sorry guys, right. I'm not sure if you remember the exponential function. Most elementary courses teach this in terms of depth or light bulbs, and I hate both. A sexy example would be the exponential PDF is telling you the distribution of waiting times. An event happens, something happens. X then refers to how long you have to wait until the next event happens. So, classic example would be stock listings on a stock exchange. At this moment, a company called Hussain Incorporated has listed on the TSX. X now represents the waiting time until the next stock listing. So, as I'll show you more in the next couple of lectures, the distribution of how long you have to, those waiting times on the next arrivals, also known as inter-arrival times, is given by the exponential. You're told that x1, x2 are independent exponential random variables. Think of them as waiting time for a stock to be listed on the TSX, and you could think of x2 as a waiting time for a stock to be listed on the New York Stock Exchange. And these are independent variables, which means the joint density can be found by multiplying the one of x1 times the one of x2, which of course take this expression up here, right? This one right here. And I now multiplied lambda e to the power minus x1 into lambda times e to the power minus x2. And you get, of course, this expression right here. The way these things work normally is, so if you actually think of the stock example, x1 could be the waiting time for a stock to be listed on the TSX. X2 could be the waiting time for the stock to be listed on the New York Stock Exchange. Someone says to you, I don't want to know the density of waiting times on TSX. I already know that one. I don't want to know the density of waiting times for stock listing on the New York Stock Exchange. I know that already. What I want to know is the average waiting time. So what they do is they define a random variable y, which as you can see right here is literally the average of x1, x2, right? So you really want to know the PDF of the average waiting time for stock to be listed on TSX and New York Stock Exchange. And for those of you who are in MFEs, you should be prepared for this in more advanced courses. Your instructor or your interviewer could simply tell you, I just want this PDF. I want the density of waiting times, average waiting times. Okay? And that's it. The trouble is, you remember that you have two x's, x1, x2. And so the only way you can get f of y1 is to first find out f of y1 and y2. But there is no y2. The interviewer only gave you y1. So when you only have y1, you have to invent a y2. And that's what I meant by the words often y2 has to be artificially defined because most settings will give you y1. But to find out the joint density, to find the density of y1, I have to first find the density of y1 and y2. So it's always in your interest to actually make up something, right? So you could define as x2, right? So let's define x2. And the advantage now is that I can now express x2. I can now invert this. So here's x2 in terms of quote unquote y1, y2, was actually in the end equal to a function of y2 only. And here's x1 rearranged in terms of quote unquote y1, y2. And what did our formula say? It said to find the density of y1, y2, what's y1? Average waiting time for TSX listings and New York Stock Exchange. Y2, of course, is x2. which in our example would be waiting times at New York Stock Exchange. What's the joint density? Wherever you saw an X1, take the joint density of X1, X2 right here. Wherever you see an X1, replaced by X1 in terms of Y1, Y2. Wherever you see an X2, replace that by X2 in terms of Y1, Y2, and then the Jacobian. So let's go slowly. What's the density of X1 and X2? That's equal to lambda something right here. Lambda squared, right? So this is in fact exactly what you see. I have the worst. Sorry guys, I'm not a, what can I say? Not the world's best artist right here. This way, there we go. Here's lambda squared, there's lambda squared. E to the power minus lambda, e to the power minus lambda. The first term is x1, but x1 of course is 2y1 minus y2. You can see that from right here, right? Plus x2, but x2 of course is defined as y2. And then of course you can verify for yourself that this is in fact, exactly the term that you see over here. I'll now go over to the next slide. So that's exactly what we saw in the previous slide. I take the determinant, absolute value, 2, right here. So this now gives you the joint density of Y1, Y2. Y1 was the average waiting times on TSX and New York Stock Exchange. Y2 was the waiting times of New York Stock Exchange. The joint density is 2 lambda squared e to the power minus lambda 2 Y1, where Y1 is in fact the average waiting times. But if I just want to get just the distribution of Y1, I have to integrate this joint density against all values of Y2. Now, if I sub this in, here's the expression. For me to carry out this integration, I have to know what the range of integration is. Now things get really dangerous. X1 was a number that could be bigger than 0. X2 was a number that's bigger than 0. The hard part of these problems is not this part. That's the easy part to do. Like this is the easiest part to actually do this stuff. The extremely hard part is finding out the ranges. And now, purposely, I remind you, I do x2 first. X2 I know is y2, but I know that x2 was bigger than 0 because I was told this in the previous slide. Because x2 is bigger than 0, I know y2 also has to be bigger than 0. So we're going somewhere. Y2 has to be bigger than 0. Okay. X1 from the previous slide is 2y1 minus y2. Since I know x1 has to be positive, that means 2y1 minus y2 has to be positive. And if I set 2y1 minus y2 to be bigger than 0, I get that 2y1 must always be bigger than y2. Why am I saying this? Because what you have here is y1, y2, and there's a surface up here. In terms, that's your joint density. This surface has the equation that you see over there right here, right? That's the equation. You want to find out just the density of y1. So what you want to do is you want to imagine picking any value of y1. Once you pick any value of y1, you want to integrate across all possible values of y2 against all possible values of y2. See, like this, you're finding the area under the curve. Pick any value of y1, for example, this one right here. Again, this is notation. When you integrate across all values of y2, y2 has to go between 0 and at most 2y1, right? Because you can see that y2 cannot be more than 2y1. So y1, y2 has to be bigger than 0, but also has to be less than 2y1. So if I carry this integral out, right, I take the joint density, integrate from lower end of y2 is 0, all the way to upper end of 2y1. You really should do this, by the way. You get this answer right here, right? Right over here. And now this is now defined for y1 bigger than 0. And y1 being, of course, let me just think for a second. Sorry, y1 has to be bigger than y2 divided by 2 and all the way to infinity, right? Because like this, right? And you can, without cheating, you should see why I said that y1 has to be bigger than y2 divided by 2 and at the very lower bound and then all the way to infinity, right? So you can check that this answer is correct. I've done it for you in Wolfram, but you should do it by hand first to make sure you do this. And by the way, you should be able to derive f of y2 on your own. What would you do? You would take the joint density and you would integrate that expression with respect to y1. And the answer you get, if you do it the hard way, integrate this, right? So you will integrate that expression, but you will do so across values of y1. That should give you this thing over here. But since you know x2 is equal to y2, the answer you get doing it this way must be exactly equal to the answer that you get that you knew this way. So if you do the math the right way, you should find that the density of y2 is lambda e to the power minus lambda y2. Right? That's the hard part. So now comes an even harder problem. This is an example of what you'll see on a test. This is your good old friend, your density, 3x, defined on this weird support over here. Remember this? Now I've actually outlined these boundaries for a certain reason. Someone tells you, you know the joint density of x and y, 3x. Someone defines a brand new variable called z1 and asks you to find the distribution of z1. And z1 is defined as x plus y. If they don't tell you anything else, which is probably what's going to happen in the test, you then have to invent a brand new variable because you have two random variables here. For me to use this trick, I need two more random variables. So why just define z2 to be equal to simply y? I can then express y as, of course, in terms of z2. I just did this 2 seconds ago. I can express x in terms of z1 and z2. And then by the same trick that I used before, the joint density of z1, z2 is, oh shit, sorry, this should not be there. Sorry, guys. Well, it can be there, but take the joint density of x, comma, y, and then multiply by the Jacobian. So let's go slowly. What's the joint density? The joint density is 3 times x. So here's your 3, there's your 3. Now I need to multiply by x, but of course I know that x is equal to z1 minus z2. So that's your 3 times x, the joint density, right, of x and y, into the Jacobian. That's the answer right there. Now, that's the joint density of z1, z2. But the trouble is, you need to find out the support, because once you have the support, you can find out just the density of z1 and just the density of z2. What becomes easier is to notice that you have all these weird borders, right? Which I will bring, I believe, to the next slide. Thank the mighty Lord. All right, let's start with this border first. I've done it in red for you. How nice. Notice that there's one border where x is equal to 1. When x is equal to 1, since z1 was x plus y, then since in that border x is always equal to 1, that means that z1 must be equal to 1 plus y. If I rearrange this, I get that y is equal to 1 minus z1, but y was z2, so you get the expression that z2 is equal to z1 minus 1. Now along the purple thingy, this thing right here, y is equal to x. Y is equal to x. And now again, z1 was x plus y, right? X plus y. And so that implies that, of course, since you have, let me just see very quickly, because where did this come from? This came from the fact that, sorry, maybe I'm misreading something. X is equal to y. So if x is equal to y, you can see how I have brain freeze right now. You have, where did it go? Where did it go? Where did it go? Oh, sorry, my bad, idiot. Right here, right? So z1 is equal to x plus y. And of course, you now have that from this expression, x is equal to y, so x is equal to y. So z1 is equal to 2y, but since y was z2, That means that z1 is equal to z2 right here, which of course implies that z2 is equal to half z1. So I've used a red boundary to say something about z1, z2. I've used the purple boundary to say something about z1, z2. And now I have the blue boundary where I know the y must be equal to 0 between 0 and 1, right? So that means that z1 must be between 0 and 1, right? Because at that point z2 is equal to 0, so that means z1 must be between 0 and 1. Right? That means now, using those things we got, this is the weird boundary. So z1 has to be over here between 0 and 1. That's that thing that we saw earlier, right? And this thing over here. Now this is pure hell to work out because what I forgot to draw here, which I'll draw on your slides, is an f of x, z1, and a z2, right? So what you're doing is, if you want to find out, if you want to find out this is a legit density, for example, you would have to integrate in this area. So you would have to break up this region into different parts. And that's exactly what I've done over here, right? So I'm going to leave this as an exercise. You should then work out how and why I managed to break up this giant thing that looks like a dagger. I'm going to integrate on this over this region, right? I broke it up into two parts, right? Part one and then part two. And I've done them separately. So once you do this, you notice that the answer in fact is equal to one. That was not very easy, but I've done it on purpose. So it forces you to see if you were given something like this, how would you and you were asked to integrate this area, how would you break up the integral so that you can do it this way? And it shouldn't be surprised that it should be something like this area, right? And then plus that area, right? Thank you very much.